what we're looking at today is, and we're going to be using synthetic division a lot. So for those who don't remember it, we're going to spend a lot of time reviewing it and going over it. It really is an extremely, once you get the hang of it, it's a great process. It's really easy. I mean, it's multiply, add, multiply, add, multiply, add. It's not bad at all. But this is kind of where it's leading, and it's the rational root theorem. And again, this is something that you do cover in Algebra 2, but a lot of people don't remember. Basically, in any polynomial function of a general form, if they're going to be roots that are rational, again, remembering the key, our Greek and Latin roots, ratio, right? Rational means a ratio number. Can be expressed as two whole numbers as a ratio. If there are rational roots to a polynomial, we can always, there's a limited number, and it's based on the leading coefficient, an, and the constant term, a naught. And yes, I go with the British saying, instead of a0, I call it a naught. Because it just sounds cooler. Something sounds like donut, a naught. And donuts are awesome and wonderful. Okay, digress. So basically, any rational roots for this polynomial will be in the form p over q, where p are the factors of a naught, and q are the factors of the leading coefficient, an. So if any rational roots exist, that's where they're going to be. And basically what we're doing is we're learning different ways of ferreting out roots for polynomial functions of degree higher than 2. We never have to use this with quadratics, because we have the quadratic formula, which automatically gives us the roots if we need it, right? If you have a quadratic, don't use this. Don't do this. It's just use a quadratic formula. You'll always get your roots. You'll be happy. Everyone's happy. If you have a cubic, see if you can group it, see if you can do stuff with it. But cubic and above, a lot of times you can't find all the roots very easily, and the rational roots theorem is going to help us. So if I have some polynomial, it starts out 5x to the 8th plus, and then a whole bunch of muddled stuff in the middle, and then with a constant term of 6. And I want to see if there are rational roots to this polynomial. What I do is I look at that constant term, 6, and the numerators for my rational roots have to be factors of 6. Factors of 6 are positive, negative 1, 2, 3, and 6. So if there are going to be any whole number roots that go into this, it's going to be positive or negative 1, positive or negative 2, positive or negative 3, or positive or negative 6. Those are the only possible roots for that polynomial. Whole number roots. There could be rational ones. So we also have the q, the denominator. Denominator are factors of the first. So the possible values are q are plus or minus 5. So when I look at this, my total list of possible roots winds up being positive or negative 1, positive or negative 1/5, positive or negative 2, positive or negative 2/5, positive or negative 3, positive negative 3/5, positive negative 6, and positive negative 6/5. So from all the numbers that exist, which is infinite, and all the rational numbers that exist that are infinite, we can narrow down our possible rational roots of this polynomial to those 2, 4, 6, 8, 10, 12, 14, 16 values. 16 seems like a lot. But to go from infinity to 16 is quite a big reduction. Now we just have to start checking and see if anything works. Now, there are a few tips and tricks we can use along the way. But what we're going to do is we're going to use synthetic division to make this process useful. And the nice thing is whenever we do synthetic division, we're getting information about the function. Because every time we do that synthetic process, we get the coordinates of a point in the function. In fact, a lot of times we call it synthetic substitution instead of synthetic division, just because it's a really easy way. If I have a big polynomial, rather than taking something to the 5th power, then the 4th power, then the 3rd power, I can use this synthetic process to find coordinates of points. It works really great. In fact, let's just look at that for a second. Oops. There's a cubic function, okay? And before we list the rational roots, I just want to show you the power of this synthetic thing. Let's say I wanted to find f of 5. What we'd have to do right now is have to substitute in 5, right? We'd say, okay, that's 3 times 5 cubed plus 9 times 5 squared plus 5 minus 10. Then I'd have to take 5 cubed, which is 125. 5 squared is 25. And we'd have to do that, so it's 375 plus 9 times 25 is 225 plus 5 minus 10. So that's 600, 605, 595, right? Okay, not too bad with 5, but it takes some time. What synthetic does for us, so anyway, we just got the point 595 on this function. That's a fun point, isn't it? You have to graph it. What synthetic does for us is it gets us the same result using the synthetic process. Again, what we do is we look at the coefficients of the function, including the constant term, and we write them down. If there are any powers of x skipped, we do need to put zeros in for those coefficients. Here there are no powers of x skipped, so we're okay. So I put in my coefficients, 3, 9, 1, and negative 10. And then the value I want to substitute into the function, 5. And now I'm going to use the synthetic process. 3 just comes down. 3 times 5 is 15. Then I add. 9 and 15 is 24. 24 times 5 is 120. 1 plus 120 is 121. 5 times 121 is 605. Negative 10 and 605 is 595. Ta-da. The synthetic process is a way of finding the coordinates of a point in the function. Whatever, it's the same as substituting in with a polynomial. So 595 is still my point, isn't it? And what we're doing with this process is this is a quick way of substituting in values and seeing if any of them give me a 0. Because if I get a 0 here, first off, we're required to put a smiley face in the 0. Don't test me on this. I will take off points on your test if you get a 0 and you don't put a smiley face in it. Because zeros make us happy. But if I get a 0, that means I found a root of the function, haven't I? Because the y value equals 0 when we have a root. I mean, any root is whatever the x value is, 0. So what we can do is we can very quickly, with this process, test numbers to see if something's a root of the function. And if it's not a root of the function, at the very least, we get information about a point. That's 595. So it's just a quick process of doing it. And again, the process is pretty simple. This number comes down. We multiply and put the result there. Then we add to get this result, multiply again, put the result there, add, multiply, add. So the process is just multiplying and adding, multiplying and adding, multiplying and adding. So for those who don't remember it, is that seeming pretty simple? It's not too complicated. It's just a really nice process. And it's a great shortcut, especially when we get these higher power functions. Especially when we start getting to the 4th power and the 5th power. Yeah. Okay. So the question here isn't asking us to do that. I just want to demonstrate that. But the question is, let's just list the possible rational zeros for this function. Don't test them. Let's just make a list. So the numerators have to be the powers of 10. So for p, or not the powers, the factors of 10. What are the factors of 10? Well, 1, 2, 5, and 10. For the denominator, what are the factors of 3? 1 and 3. So my possible solutions are positive or negative 1 over 1, or positive or negative 1. Sorry, don't want that to belong down there. And then positive or negative 1/3. Positive or negative 2 over 1. Positive or negative 2/3. Positive negative 5 over 1. Positive negative 5/3. Positive negative 10 over 1. And positive or negative 10/3. Now, I just tried 5 and I got 595. And you'll notice that all these numbers were bigger and kept positive and kept getting bigger. Do I even need to bother trying 10? No, 10's not going to work. Once I get all these numbers across are positive, all the results are positive, same sign, we call it an upper bound. And I don't need to try any number bigger than that. Okay? So a lot of times, if we're looking for roots and we put a number in, and my result row here is all positive numbers, I know that that's not a root, and I know that I don't need to try anything larger than that. Nothing larger is going to work. So we can eliminate choices really quickly. Another trick. If I look at these digits, and I add these digits up, and the sum of these digits, the coefficient, is 0, then 1 is going to be a root. 1 is going to work. So there are all sorts of little tricks we can get from this synthetic process. Now here, 9 plus 1 plus negative 10, that gave me 0, but I got that 3 up front, so no. 1 isn't going to work there either. Every time we put something in, since I get the coordinates of a point, if I am positive, if my result is positive here at 5, but was negative, say, at 2, that means there's a root between 5 and 2, right? Because it went from positive to negative. Might not be rational, but there's a root there. Yeah. Factors of negative 10. Factors of 3. So the P, here, I'll highlight them. The P comes from the negative 10. The Q comes from the negative 3. Okay? So P comes from the constant term. The Q comes from the leading coefficient. But this one isn't define the roots, it's just list. Let's just list the possible rational roots for this. We don't want to solve it, we just want to list it. So for the numerator, I want the factors of 27, which are 1, 3, 9, and 27, right? Denominator, factors of 9, which are 1, 3, and 9. I'm not putting plus minus here yet because we'll add that in a second. So I get plus or minus 1 over 1 as a possible root, plus or minus 1/3, and plus or minus 1/9. Then the 3, plus or minus 3. Plus or minus 3/3 is 1, so I don't need to relist that. 3/9 is 1/3. I don't need to relist that. Oh, happiness, fewer fractions. Plus or minus 9. 9 over 1. 9 over 3 is plus or minus 3. Don't need to relist that. 9 over 9 is 1. Don't need to relist that. It's already up there. And then plus or minus 27. 27 over 1, 27 over 3 is 9. Got it. 27 over 9 is 3. Got it. Those are all the possible rational roots of that polynomial. So now, those are the numbers I would start plugging into my synthetic division if I really wanted to find the roots to see if any of them worked. Little hint. Almost never start with these big numbers. They almost never work. Sometimes, pretty rarely, but like 27, I won't even bother. Positive or negative. Probably not the 9 either. Those probably are not going to give us roots. Those are probably not going to be valid. Those are probably not going to get solutions we want. They aren't going to give us zeros, probably. Probably. I'm not saying absolutely, but probably when you have really big numbers like that. And if we were going to set up the synthetic, remember we'd have to leave blanks for the open spaces. So 9, 6, x to the 6th, x to the 5th, x to the 4th, x to the 3rd, x to the 2nd, x to the 1st. That's what my synthetic would have to look like, because I have to account for all those powers of x that are missing. They're not missing, they just have zero coefficients. And then what we do is you just start trying something. I know 1 is not going to work because 9 plus negative 5 plus 27 does not equal 0. So I don't even have to try 1. It's not going to work. Let's try negative 1. Let's see where we wind up. So that gives me a 9. Negative 1 times 9 is negative 9. Negative 9. Positive 9. Positive 9. Negative 9. Negative 14. Positive 14. Negative 14. Positive 14. And 2741. It's not a 0. I did not find a root. However, I did find that the point negative 1, 41 is a point on this function. Okay, so I'm not completely empty-handed. Well, gosh, negative 1 didn't work. How about, and this is kind of what the process looks like, how about 1/3? So 9, 0, 0, negative 5, 0, 0, 27. 9. Well, 1/3 of 9 is 3. 3. 1/3 of 3 is 1. 1/3 of 1 is 1/3. Oh, that's not going to be fun. Negative 4 2/3, which would be negative 14/3. So it'd be negative 14/9. Negative 14/9. I'm sorry, positive. I'm multiplying by positive. Yeah. 1/3. I'm doing okay. Okay. Negative 14/9, so it's a negative 14/27. 1/3 of that is negative 14 over 81. I get 27 minus 14 over 81, which is going to be very nearly 27, 26 point something. Okay? So not a 0, but I now know another point, 1/3, 26. So I know between negative 1, 1/3, it seems to be decreasing. And we can start plotting points and getting ideas about functions. That one wasn't going to come out nice. Actually find the rational zeros of this function. Now this one's nice because it has a leading coefficient of 1. Just like with the old polynomials, whenever you get that leading coefficient of 1, that's awesome. Because that means I have no denominators, which means there'll be no fractions. How many will be happy by the fact that there are no fractions? I'm happy when there's no fractions. Not that fractions are bad, it's just that they're harder to work with. So my possible roots are plus minus 1, 2, 4, or 6, no, factors of 8, sorry. 4, and 8. Those are my possible roots. I only have 8 possible roots. When I set up my synthetic, I've got 1, 3, negative 6, negative 8. First thing I check, do these digits all add up to 0? No, they don't. So that's unfortunate. If they did, 1 would be a root. But let's just go ahead and try some stuff. What number would you like to try first? 2. Okay, let's try 2. Bring down the 1. 2 times 1 is 2. 3 plus 2 is 5. 2 times 5 is 10. Negative 6 and 10 is 4. 2 times 4 is 8. Aha! Happy face. Now, I've found that 2 is a root, which means x minus 2 is a factor. Right? What is the remainder at this point? Well, now this is where this comes in really handy. Once I have that, what's left here, these are the coefficients of what we call my diminished polynomial, or x squared plus 5x plus 4. This is the factorization of that. Okay? If I factor this polynomial, this is how we would start. And these coefficients are coming from the results of my synthetic division. And then I just factor this further if I need to. So that would be x plus 4, x plus 1, because that factors nicely. So my roots are actually at 2, negative 4, and negative 1. And we're done. I found all my roots. I don't have to continue with the synthetic once I found that 0, because I was down to a quadratic, which I can factor or put in the quadratic form or whatever I need to do. And that one was an easy one to factor. Does everyone see where this polynomial came from? Came from the coefficients that were left here. And x minus 2 is the factor we got from the 2 being up here. So I've just found all the zeros for that function are 2, negative 4, and negative 1. Yay. A little bit tougher. But again, we have a 1 for a leading coefficient, which makes our life happy. So my possibles are 1, 2, 5, and 10. I only have 8 possible rational roots. How many roots are there going to be for this polynomial? There are going to be a total of 4 because it's next to the 4th function. I don't know if any of them are rational. They might all 4 be complex for all I know. But we start setting up. My coefficients are 1, negative 3, negative 11, 3, and 10. And notice anything? 1's going to work, isn't it? Because negative 3 and negative 11 is 14, 1, 3, and 10 is also 14. 1 is going to be a factor here. It's going to work. 1 times 1 is 1. Negative 3 and 1 is negative 2. Negative 2 is negative 13. Negative 13. Negative 10. Negative 10. Happy face. I've just found one of the rational roots. X minus 1 is a factor. And we're left with x squared minus x cubed, minus 2x squared minus 13x minus 10. Oh dear, that's not going to factor nicely and easily probably. So we have to start again with synthetic, now with this polynomial. It's got the same possibilities, so we're just going to use that as my new key. 1, negative 2, negative 13, negative 10. Now you have to be careful, since we're doing this polynomial, I'm no longer getting points on this function, am I? When I plug in. Because it's a different function. It's a factor. We're factoring a factor now. So I don't want to confuse that as actually finding points on this original function anymore. But again, we start trying. Not going to be the 1, but we can try our other terms. What would you like to try? 2? Negative 2? Negative 1? Pick something easy. 2, okay? 2, 0, 0, negative 13, negative 26, negative 36. No, 2 didn't work. So let's try 1, negative 2, negative 13, negative 10. What do you want to try next? How about negative 2? I don't know. I'm just guessing 2. Negative 2 gives me a negative 4. Positive 4 gives me a negative 9. Positive 18 and 8. Okay. Well, I don't know. I know now that 2 doesn't work and negative 2 doesn't work, but there should be a root somewhere in between there because it went from negative 36 to positive 8, right? Yeah. Oh, you're right. I boo-booed. I'll blame it on the cold. How about that? Oh, and then it works, doesn't it? Happy day. Fantastic. So now I know a second root. So I have x minus 1 from up here, x plus 2, and now I'm left with x squared minus 4x minus 5. Oh, that's going to give me x minus 5, x plus 1. And I've completely factored that polynomial. I know the roots are at 1, negative 2, positive 5, and negative 1. Gosh, we had 4 out of the 8. We could hardly go wrong. Unless you make a mistake. Are you getting the idea of the synthetic a little bit better now? In the way that it works? Here's another one. Again, very limited choices. 1, 2, 3, and 6, positive or negative, right? Coefficients are 1, negative 2, negative 4, 11, and negative 6. And 1's going to work again, isn't it? Because if I add those stuff, I get a 0. 1, 1, negative 1, negative 1, negative 5, negative 5, 6, 6, happy face. By the way, zeros only get a happy face at the end, not in the middle. It's very important. Keep track of your happy faces. So now we're going to try this polynomial. So I know I have x minus 1 is one of my factors. We've got that one. 1 is a root. So now we're going to use this polynomial, 1, negative 5, 6. What do you want to try with that one? Again, I've got the same choices, plus minus 1, 2, 3, and 6. I know 1 is not going to work this time. 2, okay, let's try 2. So 1, 2, 1, 2, negative 3, negative 6. You're good at this. Excellent. I now have my second factor. I have x minus 1 and x minus 2. And I'm left with x squared plus x minus 3. Oh, that's not going to factor, is it? So if I want to find my other roots, they aren't going to be rational. And how can I tell they aren't going to be rational? Well, because it would factor if they were. But the other thing I could do is I could take this and put the discriminant in, b squared minus 4ac. So that'd be 1 squared minus 4 times 1 times negative 3, or 1 plus 12, which is 13. So it's going to be plus or minus the square root of 13 when I put that in the quadratic formula. That's not going to simplify, is it? My other roots are going to be at negative 1 plus or minus the square root of 13 over 2. If I put it in the quadratic formula. But those are not rational roots. They're irrational. They argue over the silliest things. They're just irrational. But we found both our rational roots at 1 and 2. So again, it's a way of figuring out what's going on with polynomials. Yeah?
So then you don't even worry about the other ones? You just, if that was a question on a test, you just put...
If it said list the rational roots, it would just be 1 and 2. If it said find all the roots, then you'd want to find the last two. And we can only can because it's quadratic. And we can use a quadratic formula. Oh, leading coefficient, yay. 4x cubed minus 12x squared plus x minus x plus 3. So 4, negative 12, negative 1, 3. My choices are a little bit more broad this time. I'm going to get some fractions. But I usually don't start with my fraction choices. 1 is not going to work. My only whole number ones are going to be 1 and 3, right? Positive and negative. So which one would you like to try since 1 is not going to work? Anyone not understand why 1 is not going to work? Because they don't add up to 0. Now, does that mean we don't put 1 in to find out what the y value is when x equals 1? Maybe we do, just for information's sake. Even though we know it's not going to get to 0, it's still going to get to a point on the function. So sometimes we might actually use it even though we know it's not going to work because it's easy and it gives us information. But since we don't have 1, let's try negative 1, just real quick. 4, negative 4, negative 16. 16, 15, negative 15, negative 12. Okay. That doesn't give me a root, but it does tell me the point negative 1, negative 12 is the point on this function. Let's try positive 1. Let's see what it tells me. 4, negative 12, negative 1, 3. So 4, negative 8, negative 8, negative 9, negative 9, negative 6. Okay, so 1 is at negative 6. Guess we got to keep trying. Haven't found out anything interesting yet. Whoops. I just want to extend the page. I guess we could try 1/2. 3? Okay. 4, negative 12, negative 1, 3. I think she's on to something. Aha. There we go. So x minus 3 is a factor, which means my other polynomial here is 4x squared minus 1, which is going to factor nicely to 2x plus 1, 2x minus 1. So my other factors are negative 1/2 and 1/2. I'd have gotten it with 1/2 too, so don't be all like, ooh, Martha, you're so off. 1/2 would have worked. But that's what we're about today. I mean, and like I said, that's why I knew kind of we had this coming yesterday, so I wasn't panicking too much when people didn't know the synthetic process. Are you more comfortable with it now? Do you like it? I think it's awesome. I love synthetic substitution. It's a real shortcut. All right. All right. That's it. The homework. And some of you have to go pick up yesterday's homework a little bit, but that should be made easier now by what we did today. Page 206, 12 through 24, even 30 and 30 through 32. And then tomorrow and Monday are both review days, and Tuesday is our next quiz. All right?